So hello everyone. It's great to be here. My first time coming here. Normally I've deferred to Thierry to present on the 3D modeling in Southern Ontario. But this was an opportunity to talk more generally about the hydrogeological framework for Southern Ontario that's being developed. So just a quick acknowledgement of my co-authors. So Thierry is probably familiar to you all. Steve Fry, who's with Aquanty and the University of Waterloo, hydrogeological modeler. Charles Logan, who was the leapfrog operator modeler at the Geological Survey. Jordan, who you certainly all know. And Melissa, who's a hydrogeologist at the Geological Survey. So quick acknowledgements here is particularly to NWMO for funding stage 2 of the 3D model development. And some of the individual contributors, and in particular to Frank at the OGS for his insights into the Paleozoic geology. So as you all know, and we don't really need to go through this in any kind of detail, but there are a lot of social economic drivers in Southern Ontario. Oil and gas is just one of those. There was a time when low-level and high-level nuclear waste was a consideration. Storage issues, waste disposal, aggregate, and of course potable water. And then agriculture is a big impact on shallow groundwater. So why did I come and work in Southern Ontario with the Geological Survey of Canada? We had a program on mapping 30 key Canadian aquifers, and a number of them were in Southern Ontario. The Upper Thames was identified as one, the Waterloo Moraine, the Credit. And when you have no money to work on individual subjects, your mind immediately goes to, well, let's work on the whole area. So we decided to focus on 110,000 square kilometers of Southern Ontario, basically all of Southern Ontario, west of Kingston and south of the Canadian Shield, excluding Manitoulin Island. And it was good timing at the time. So this project originally started back around 2014. And there was considerable interest following source protection that came out of the O'Connor report, which was the result of Walkerton on groundwater management and source protection. And the Environmental Commissioner for Ontario had made the following statements in a publication, and that data management was a real problem in Ontario for groundwater. And actually the Oil Gas Salt Resource Library is a model, I think, of well-curated data with a vision and a foresight and a vision of the utility of data management. So in a nutshell then, we're going to walk from the state of chaos that existed before this modeling to a lithostratigraphic geological framework for Southern Ontario that moves to a hydrostratigraphic framework, which then led to a fully coupled integrated groundwater surface water numeric model. And then we may touch on, hopefully, the application of GRACE. And the timing of this work was rather appropriate. There's a lot of interest internationally and in Canada to look at how to better manage subsurface resources, competing issues. And one of the steps or stages in that exercise is the development of 3D models. Fortunately, it's easy to build a 3D model. The question is, what's the integrity of that 3D model? And fortunately, there's a well-developed geological framework in Southern Ontario and a hydrostratigraphic framework. This highlights just some of the public documents that are available on that subject. And working with Thierry and Frank provided a good connection between the literature and practitioners. So we started off by building a lithostratigraphic model. We built a 4-layer model to start with as a proof of concept and to encourage our managers to fund us. We then moved to a 54-layer model at a 400-meter grid scale, and it incorporated the available digital data from the Oil, Gas, and Salt Resource Library, water well records, section information from escarpments and outcrop mapping. And we did a reasonable amount of QA and QC that was possible within the funding framework. From that 54-layer lithostratigraphic model, we moved to a 14-layer hydrostratigraphic model that was based both on water quality or water chemistry derived from the petroleum library and lithological information. And you can see here quickly the different water chemistry layers in the model that help constrain the definition of the hydrostratigraphic units also. And to make the model more attractive and applicable to a broader audience and client group, we also brought in information on hydrocarbon intervals, gas and oil, showings in the library database, and then we discretized that actually into the model framework to make it complete. And of concern often from users of models is what's the integrity of the model? Can you provide me with any kind of confidence interval on any one discrete grid cell in the model? And we applied a relatively simple approach to this, looking at mostly distance from well information. And this is just an example of the discretization of that confidence for a couple of different layers here. Obviously, you can see there's a strong correlation between southern Ontario and north of Lake Erie, where there's a lot of data, and moving northwards and eastward where there's considerably less data. So that hydrostratigraphic model then provided a framework for us to build a numeric model, fully coupled with groundwater, surface water. And we built two versions of that model. One that went all the way to the Precambrian, has a relatively coarse discretization, uses effectively fourth order streams as the metric to support the discretization. And then we looked at the realistically, with the knowledge from NWMO work, how deep was modern groundwater likely to circulate? We don't really need to model to the base of the basin. So we modeled to the base of brackish water. And that allowed us to improve the spatial resolution. So that incorporated third order streams and moved the finite elements down to a finer scale. And this is all published in a summary report that came out in 2020 by the GSC. All of the models are actually in the public domain. So they're available through the open file system of the Geological Survey. They're available through Jordan at the library. The public domain part only allows really importation into other software or viewing. You can't actually interact with the underlying data, which is the proprietary basis for the library. So that brings us to GRACE then. We're interested in groundwater storage flux or change over time. And GRACE is the Gravity Recovery and Climate Experiment. And this graphic just quickly highlights how GRACE works. It consists of two satellites, and they respond to the gravity field on Earth. So if there's an increase in gravity, the first one speeds up, separates the distance between the two satellites, and then as the second satellite arrives at the gravity high, it accelerates and reduces that space. And they integrate a signal over 1 month period to provide a snapshot of the gravity field. And the highest temporal change in the gravity field is related to water storage change. Of course, excessive petroleum production could also produce a change in the gravity field. And we've discretized or reprocessed the data from JPL and NASA to Canadian watersheds to make it more amenable. And we're integrating that work with the numeric model for Southern Ontario. So GRACE is a very large course methodology for looking at water storage change. Has a footprint of about 300,000 or 300 kilometers long, so about 100,000 kilometers notionally. And it only gives you total water storage change. You can't look at the change in soil moisture, snow, surface water, groundwater. And that's where integrating it in Southern Ontario with the numeric modeling allows us to partition that total water storage change into the components. And you can see some of the components being highlighted in the lower left there. In the right-hand side here, you see that we have both good temporal correlation between the numeric modeling and the GRACE signal, and also relatively good amplitude for the most part. So Jordan talked about visualization and interacting with the 3D models. You can see all of the physical models in the room next door. We've also been working with the Polish Geological Survey on how to make the model more accessible through web viewers. And we currently have the surficial sediment model, which is an 8-layer model of the surficial geology. The bedrock, all 54 layers you can stream, and also the hydrostratigraphy model is available. The hydrostrat model, you can actually cross-section, you can interrogate and produce synthetic boreholes, or you can bring up all of the OGS, or oil, gas, and salt resource library boreholes that are over 500 meters deep, and you can interrogate those, and it will take you to the metadata records at the library. And then depending upon your membership status, and et cetera, you can continue to interact with that data. So in summary then, we've constructed I think what we could consider a relatively robust geoscience framework for the subsurface of southern Ontario. It supports improved subsurface management of resources. It can be used to help in terms of conflicting land use and subsurface usage. It was only possible to build this model because we're in a petroleum producing sedimentary basin. And a lot of these models, if you look across Canada, Saskatchewan now has a similar model. Alberta led the way in terms of construction of a large framework model. And they're all predicated on the accessibility to subsurface data produced by the petroleum industry. And unfortunately, integration of seismic data wasn't possible in this case. Maybe in the future, that's an additional enhancement that may be possible. So thank you very much.